Hello, everybody. So we have taken the information from Module 3 and divided it into two modules, or two presentations, I should say. And what we're going to do now is we're going to kind of take all that we have learned up to this point and apply it to looking at individuals and describing individuals. And so what that means is we have looked at descriptive statistics when we were given a set of data, the mean, median, and mode. And we have looked at some measures of dispersion as a result. So the mean, median, and mode told us how our data are gathered around the center. Measures of dispersion, the range, variance, and standard deviation, told us how far apart those data are spread. Okay? So the next step then is we're going to take the mean and the standard deviation. So the mean, or not the variance, remember, was the average distance from the mean, and we did a sum of squares to get that. But that's really telling us the average distance from the mean. And we standardize that in what we call the standard deviation. Now we're going to look and see why we did that. And we're going to be able to take individual scores, no matter what it is that we're measuring, and standardize them and tell where all individuals are. Okay? So this is very exciting. It's kind of a big culmination of the first part of our course. So with that said, let us look at our goals that we have for this module. Number 1, describe in terms of the mean and standard deviation, z-score and t-score numerical distributions. Given a set of raw scores, transform them into corresponding z-scores. Convert a set of z-scores into a distribution of t-scores. Convert a set of z-scores into a distribution of standard scores with any given mean and standard deviation. We're going to we're not going to stress that one very much, but it can be done. Interpret the meaning of an individual standard score relative to the distribution of concern. Describe the characteristics of the normal curve. This is getting exciting. Given a set of z-scores and using characteristics of the normal curve, convert the z-scores into percentile equivalents. And then finally, given a percentile score and using the characteristics of the normal curve, transform the percentile into a standard score. So let us begin then, and we'll come back to these goals at the end. So here's a scenario. If a student comes home all excited and says, I made a 65 on an exam out of a possible 80 questions, does the student have a right to be excited? What if the student said the mean in the class were 48 and the standard deviation was 8.5? Can she be excited? So what we can remember is the standard deviation, and we're going to quickly review that in a minute, is the distance from the mean. So if the standard deviation in these test scores was 8.5, the student got 65 and the mean was 48, she's 17 points above the mean, or 2 standard deviations. Okay? Let me tell you that she can have a right to be excited. And we'll understand that when we look at the normal curve, okay? So you can see how we're going to start pulling these things together now that we've kind of learned them. So standard deviation and mean, 2 huge important things here. Let's take another example. Consider if an average American male weighs 172 pounds. What percentage of American men weigh more than 250 pounds if the standard deviation in the United States, this is in the United States, is 29 pounds? how can we learn that? Okay? So basically, that's what we're going to do. We're going to answer some of these questions. We'll examine how individual scores compare to others in this section. Whether it's a score such as getting 65 out of 80 and looking at the whole class, or whether it's an American weighing 250 pounds and trying to figure out how many people weigh more than 250 pounds in the United States. Okay? That's what we're going to do. So how do we do it? We will use the mean to serve as an anchor in what we're doing. And we all understand the mean. This is the most common thing that we refer to as average. So we're not going to explain that anymore. And we'll use the standard deviation as the yardstick to measure individual performances. So those are the two important things that we're going to remember and move forward with. The mean and the standard deviation. So let's take just a couple of minutes to look at the standard deviation again. So remember when we did standard deviation, we started off with variance. And in doing that, we looked at the sum of squares. Now the variance is how far individual scores differ from the mean. And so here we were looking at sit-ups that the class officers could do. And our mean for the class was 27. And so when we looked at individual scores, we saw that somebody could do 15, and we wanted to see how far they were from the mean. So 15 minus 27 is minus 12. So he did 12 less than the average person. And we carried that through with all scores. Now, if we added those together, because the last guy or girl did 38. 38 minus 27 was 11. She was 11 above the mean. So in theory, if we add all these together, if we're describing how far they are from the mean, we should get an equal number below and an equal number above. Therefore, it's going to be 0. So what we have to do then to get rid of that is we square this. Okay, and this is what we call the sum of squares. So negative 12 squared is 144. Negative 5 is 25. So that gets rid of our negative numbers. And we sum them up once they're squared. And this is our sum of squares. And then what we do with that, with our sum of squares, is we divide it by our n, our number of participants. And once we do that, we find our variance. So if our sum of squares is 344, and we divide by capital N, we get 57.33 for our variance, okay? And remember, variance is sigma squared. So that in of itself is difficult to gauge what it tells us unless we have some comparisons to go by. So what we then do is take our variance and, drum roll, we find the standard deviation. The standard deviation is simply the square root of the variance. And this is how it is written. Sigma equals the square root of the sum of the score minus the mean squared over n. That's variance in there, okay? Notice what we've simply done is taken the variance and squared it. So when we do that to our sit-ups, we find that the standard deviation was 7.57. Now, once we have that, I want you to just tuck that away, not too far, because we're going to come back and use it because it's extremely important. But now we've standardized how far apart from the mean all the scores are. Now we need to standardize the individual scores themselves. And this is a real easy process. And once we do that, we're going to go back to the standard deviation, and we're going to be able to tell a lot about every individual who we have data for. So, to examine individual performances within a group, we'll look at what are called standard scores. In other words, we're going to take our raw scores and we're going to standardize them. We'll see what that means. Standard scores will tell us two important things. How far the mean of the group, how far from the mean does an individual score fall? And whether the individual score was above or below the mean. And we're going to do this with two types of standard scores. The most popular score and the one that we will use the most in our course are called z-scores. That's a little z scores. But we're also going to look at t-scores, and that's a capital T. Okay? And computing these is actually relatively easy once we know the mean and the standard deviation. So let's look at how to compute these, and then we'll explain why they're important and how we're going to combine all this to give us some really powerful information about our data. So the most common one I said was a z-score. Now remember what I said. This is a small z, and it's important that we realize this is a small z later on. Okay? This presentation wouldn't let me change that to a small z, so just know every time we talk z-score, it's a small z. Even here, I think it's a capitalized z. So to convert z-scores, you need to have the mean and the standard deviation. So our formula is x minus x bar over standard deviation. And again, this is where this is confusing sometimes, I know. This is a capital X on each of these. So individual score minus the mean, those capital X's, that's what they mean, equals, this is a little x. So the little x is the deviation from the mean over standard deviation. So let's put this into play, what we're talking about. Suppose we have a class of 30 students who answer trivia questions. Okay? The mean for correct answers was 50, and the standard deviation was 6. In other words, the average person got 50 questions right. Our standard deviation was 6. John answered 53 questions correctly. 53 is his raw score. What is John's corresponding z-score? So, the way we do this is we just plug these numbers into our formula. So, x minus x bar right here, our score minus our mean, we have x bar is 53 minus 50. 53 was John's score, 50 is the mean, and we get 3. So that's the top half of our formula. Divide that by the standard deviation of 6. 3 divided by 6, we get a z-score of 0.5. So automatically we know, because this is a positive number, this is an indication he scored above the mean. Alright? So let's take another example here. Let us see here. In the same example, let's say Jerry only answered 41 questions correctly. His z-score would be x minus x bar, score minus mean. 41 minus 50 equals -9 for the top part, our numerator. -9 divided by the standard deviation of 6 gives us a z-score of -1.5. He scored below the mean, as indicated by our negative numbers. And we can see that really if John is at 0.5 and Jerry's at -1.5, the distance between the two is 2 standard deviations, or the distance is 12. Okay? All of this will come into play and we'll understand in a minute. So, basically, very simple on how to figure z-scores. So let's look at the characteristics then of what a z-score is and how we're going to use this. So number 1, in a symmetric distribution, about half of the scores will be positive and half will be negative. Now, we're going to see later on that not all the stuff that we deal with are necessarily symmetrical distributions. And part of that's because we're dealing with small populations. For the most part, now the little work that we're going to do today is going to look at the big picture. But when you're looking at your individual students in your class or individual students in our class, we're talking less than 30 people. So it may not be completely symmetrical. It may be skewed one way or the other a little bit. But in general, z-scores show symmetry when we're looking at the total number of scores, and we see about half of them positive and half of them negative. Most z-scores will need to be expressed to the hundredths position, and we will see that and why that's important, okay, when we look at some data sheets. And then finally, and this is really important, this is kind of the ultimate thing here. If all z-scores, or if all scores in the distribution are converted to z-scores, the mean, which here it's called z-bar, the mean is equal to 0, and the standard deviation is equal to 1. So when we were talking about those Jerry and John in their questions, and we said the mean answer correct was 50 and the standard deviation was 6. When we converted those to z-scores, then magically everything became that our mean is 0 and our standard deviation is 1. The fact that our mean is 0 and we said that half of our scores are positive and half are negative means that those that fell below the mean will have a negative z-score. We saw that with Jerry because his z-score is negative 1.5. So that brings up the next standardized score, and that is t-scores. Now, t-scores work very similarly to z-scores, but because some people don't like to deal with negative numbers or fractions, they'll use t-scores. T-scores are scaled from the z-scores, but instead of a mean of 0 and a standard deviation of 1, t-scores have a mean of 50 and a standard deviation of 10. Now, I'm a visual learner, and in just a minute I'm going to show you why all this is important and where all this fits on there, on our curve, okay, when we talk about the curve. But for now, just bear with me. You have a copy of this PowerPoint that you can download. So the formula for converting a t-score, once we have our z-score, is we're going to multiply our z-score by 10. And you can see here what this does is it changes our standard deviation from 1 to 10. And then we're going to add 50. And what that does is it makes our mean from 0. Now t-bar is 50. So let's convert those scores to t-scores. John had a z-score of 0.5. So our t-score formula is t equals 10z plus 50. So t equals 10 times our z-score of 0.5, which equals 5. We're going to add 55, and we get a t-score for John of 55. 55 plus 50. Sorry. Let's take Jerry's scores. We said Jerry had a z-score of minus 1.5. When we plug our formula in, t equals 10z plus 50. So t equals 10 times negative 1.5, which equals minus 15. And when we add 50 to that, we get 35. So notice that John had a z-score of 0.5, which in z-score, our standard deviation was 1, so he was half a standard deviation above the mean. His t-score is 55. Our standard deviation in t-scores is 10. So again, he still remains half a deviation above the mean. Okay? Make sense? So what if we had to work backwards slightly? If we had a t-score and we wanted to convert it to z-scores, well, that's very simple. Our z-score equals t minus 50 divided by 10. And we could work that out. So if we wanted to take John's t-score, a 55, t minus 50, 55 minus 50 is 5. 5 over 10 is 0.5, 1/2. So that's how we work backwards from a t-score to a z-score. So, what does all this have to do with what we're trying to learn? And how does it fit in with the stuff we've already learned about central tendency and measures of dispersion? Well, I'm glad you asked. So, let me throw out a couple of tidbits for you here that we'll look at in a minute. We know that IQ scores have a mean of 100 and a standard deviation of 15 for the general population. We also know that when it comes to the SAT scores have a mean of 500 and a standard deviation of 100. Okay? So we're going to come back to that in just a minute. So I want to throw those out to you and show you kind of get you thinking about the possibilities of what we can do once we have standardized scores. So the question is, so what now? Who cares? Who cares? You shouldn't care. If we know z-scores, and the answer is the normal curve. Everybody should care. So the bell curve or the normal curve is a frequency polygon that shows scores which are normally distributed. As one examines scores that spread from the center, the scores generally get smaller as they go either to the left in the negative or to the right in the positive. Keep in mind, we'll be looking at samples with small numbers when we're dealing with our class. So the curve will not necessarily be normal. It may be skewed. But here's an example of the normal curve. Okay, so characteristics then of our normal curve. These are important to remember. The mean, median, and mode are located at the central point. So when we talk about IQ scores being a mean of 100 and a standard deviation of 15, we're putting IQ scores on the normal curve. So we're saying the mean, median, and mode are located in the middle of the curve. The curve is symmetric around the mean. In other words, there are just as many negatives as there are positives. Sound familiar? We said this about z-scores earlier. And finally, the tails of the normal curve approach the baseline but never actually touch it. And what we see, we'll see that we have terms for these people. There are reasons why the tail never touches the baseline. So now that we're talking about the curve, let's talk about percentiles. So remember, we discussed percentiles a little bit earlier in the beginning of some of the coursework, I think in Module 2. When we looked at frequency and cumulative relative frequency, we also examined percentiles. So this is most likely familiar to you in things such as students who score in the 95th percentile. The 95th percentile, and I pulled that up on purpose because I believe it's the 95th percentile that is the most common percentile rank on a national test called the COGAT, the Cognitive Abilities Test, that is used in schools to determine if students qualify for gifted and talented. It's a purely academic test. We can see this same thing from a normal curve. Okay, this idea of the 95th percentile. And so once we can determine, so what does that mean, 95th percentile? Doesn't mean he scored 95 correct. The 95th percentile means that of all the people who have taken the test, little Johnny's score is as good or better than 95% of the people who took the test. Okay, that's what percentile rank means. It doesn't mean made in 95% of the test. It could have only answered half the questions. But if the test is so hard that people are not answering a lot of the questions, then 95th percentile may be good. Let me give you a prime example of a national test that uses percentiles that schools also use, and that's the Iowa Test of Basic Skills, your ITBS test. ITBS scores are based in percentiles, and they don't tell you what your child is learning. What they tell you is where your student or your child ranked based upon all the other 5th graders who took that test across the country, or all the other 2nd graders. So that's what a percentile-based test like the Iowa Test of Basic Skills does for you. On the other hand, when we're talking about testing for 3rd through 8th graders, we use norm reference testing, and that tells us whether or not the student learned the standard or not on which they're being tested. Okay, so it's a little bit difference there in those tests, and the power of those tests can result in telling you whether the children are learning or not. But we're running down a rabbit hole there. So percentiles tell us where the student ranks with all the others who took the test. So we are making the assumption about things being normally distributed. We're putting them on the curve. Once we do that, though, we've learned that we can convert any number of scores into z-scores. Okay? So remember, if we were to look at our z-score formula real quick, we can take any score and just subtract it from the mean and divide by the standard deviation and get a z-score. Once we do that, we can do that to a whole set of scores. We can answer these specific questions here, okay? We can answer how many scores are less than 1.28. What does 1.28 equal in the raw score? How many scores are greater than 1.96? How many scores are there between the mean and negative 6.7 or negative 0.67? How many scores are there between the positive 2.58 and negative 2.58? And what does it mean to have a score of 2.58? We can answer all those questions when we look at the normal curve, okay? So, the first step is we have to look at the normal curve. So, I have included a copy of this in your module, but let me go back and forth here and pull up this document for you to see. Okay, this is a PDF that you have in this module, and so we're going to look at this, and you have two forms here. In column A, this is our z-score. Column A is the area from the mean to the z-score. So whatever our z-score is, column A is going to tell us how far from the mean to our score it is. Column B is the larger portion, above or below. And column C is the smaller portion. Now what do we mean by all that? So let's take a look at this other chart. So you can see we go up to 3.7 here. So this is another chart that I've added here. These are just two examples of looking at the curve. And here, let's say we had a z-score of, let's take this example here, 1.45. Okay, notice, number one, it's a positive score, 1.45. The standard deviation is 1. Remember, we said in z-scores, our mean is 0 and our standard deviation is 1. So, this person's score is almost 1.5 times the z-score. Now, our mean is 0, And we talked earlier about the use of the Greek letter mu, but for all intent and purposes now, just know that this is the same as x bar. Okay, our mean, or z bar. Our mean is 0. So let's look at 1.45 and see what's happening here. So 1.45. So we can see 1.4 here. I don't know if I can. Yeah, oops, cancel. So we can see 1.4 here. And if we go across to 0.5, we see 0.4265. And that's what they've written up here, 0.4265. Now, what that tells us is we can put this in percentiles. Okay? Percentile ranking. This person, let's say this is Sherry. And Sherry's raw score on whatever test you took was 1.45 above the mean. Her z-score converted, when her raw score is converted to a z-score, she's 1.45 above the mean. When we look at the curve, we see that 1.45, there's the 5, 1.45, is equal to 0.4265. What that means is she is 0.4265 above the mean in this case. What we have below the mean, since this is symmetric, is we have 0.5000. We're going to take it to the 10,000s. So if we add the 0.5000 to the 0.4265, that tells us that she has a percentile rank of 0.9265. We can multiply that times 100 and 92.65, so she scored in the 92nd percentile. Okay? Now, let's use our other chart real quickly. So we said she had a z-score of 1.45, and the area between her score and the mean is 0.4265. And we got that by going down 1.4 and then 1.5. Oops. Gave us 0.4265. So let's go back up to the first chart. And let's find 1.45. So here's 1.45 in this chart. So this tells us then a little bit better of actually what we're looking at. So this tells us that she is 0.4265 above the mean. Since her score is positive, she's above the mean. This tells us that she's 0.9265 in the larger portion. So when we take the 0.5000 below the mean and add it to Sherry's score, she's 0.9265. In other words, she's in the 92nd percentile. Okay? There are only, if we look here at the area of the small portion, this is what's left. So if we were to go back and look at our chart real fast, this little portion here, it looks like there's a lot there. But actually, when we look at our numbers here, there's only 0.0735 if we multiply that times 100. There's only 7.35% of the population who scored better than Sherry. So that's what is a powerful tool about what we're looking at here, okay? So you have this chart in your module. So let's take a look at some other things that we can do with percentiles and the normal curve. Let's pull back up our PowerPoint. So here again, we're simply going over the stuff that I told you about the last page. So we said the 1.45, when we went through here, it's 4.4265 from the mean. And I go through this and explain to you how to use this chart. So let's work backwards. Let's say earlier we talked about the COGAT test, the Cognitive Abilities Test. And we said this is used in most districts to define GT, or gifted and talented. If a student then, if we know that a student needs to score in the 95th percentile, what is the corresponding Z-score And then what is that raw score that corresponds to that z-score should a child get in order to be classified as GT? The only thing we need to know in order to answer this question are two things. As always, we need to know what the mean of the test is and what the standard deviation. In this case, our mean for the COGAT is 100 and our standard deviation is 16. Now there are questions. People always compare this to an IQ test. You can go online and look at that. We're not going to get into, or we're not going to run down that rabbit trail right now. But the mean of our test is 100. The standard deviation is 16, and a child has to score in the 95th percentile in order to be classified as GT. What score must that child get? So how do we do this? My goodness. So the first thing we need to do then is find out what the 95th percentile looks like. So we know that the 95th percentile, it's a positive, so we're going to have a 0.5000 at the bottom. So we need to look at the closest thing to 0.4500 from above the mean. Because when we add that to our 0.5000 from the bottom, that will give us 0.95000. So we got to be in at least that range at a minimum. So looking at the chart, we just simply want to find where 0.4500 or the nearest greatest number above that is, and I've highlighted it on the chart here, and we found 0.4505. And so that's going to put us at 0.9505, and we see that corresponds to a z-score of 1.65 is how you do that. So we have to have a z-score of 1.65. So then we can look at our formula and know that a z-score is our individual score minus the mean over the standard deviation. So we're just going to work the formula a little bit backwards, do some basic algebra here. So if we have our z-score and we know what our mean and our standard deviation are, then how do we find what our actual score is that the student has to get to be considered the 95th percentile and gifted and talented academically? So our formula then says 1.65 equals our score minus 100 divided by 16. And when we work that around, we're going to multiply each side by 16. Then we're going to add 100. And anyway, we're going to ultimately get down to our score is 126.4. We're going to have to go up. So a student has to get 127 on their COGAT in order to be in the 95th percentile. Okay, that's what that's telling us. Now, earlier we said, just to get you excited a little bit, we know some basic things about IQ and SATs that give us some information. We know that a typical IQ score is 100 and the standard deviation is 15. We also know that when it comes to SAT scores, the mean is 100. I think I said typical earlier. I meant mean of IQ scores is 100. The mean of SAT scores is 500 and the standard deviation is 100. What percentage of students score 800 on their SAT? Okay. At first you're probably thinking there's no way to do this, but there is, because we've worked through it already. What percentage of students in America have perfect SAT scores? We know what the mean and the standard deviation are. So what we need to do is find our z-scores. So let's take a look at that formula. Z equals our score minus the mean over the standard deviation. Here, we know that our score we're looking for is actually the perfect score of 800. The mean is 500. The standard deviation is 100. 800 minus 500 is 300. 300 divided by 100 equals 3. So our z-score then is simply 3.00. We know from this chart, let me get my point. We know from this chart that below is 0.500. And when we look at our z-score of 3.0, above the chart we have 0.4987. So 0.500 below the mean plus 0.4987 above the mean equals 0.9987. Or when we put it in percentiles, 99.87 percentile. In other words, if we want to look at the percentage of students above that, then we're looking at 0.13%. Not even a percent. 0.13% of the students in America make a perfect 800 on their SAT. That's a pretty small number. Let's take IQ and do the same thing here. What if I told you or confessed to you my IQ were actually 82? Where would I rate in comparison to people in America? I think these numbers, these scores are from America. I don't think they're from the world, but they could be. Again, we take our formula z-score equals x minus x bar over standard deviation, sigma. We know that my IQ is 82. We subtract that from the mean. We get negative 18. Negative 18 over 15 is a negative 1.2. So we take 1.2, it's just negative, doesn't mean anything to us. What it means is that we have now 0.5000 above the mean. We're still going to add our 0.3849, and we find that we come out 0.8849. This means that my IQ of 82 puts me in the range, in the 0.1151 range. We can subtract that from 1. Or that 88.5% of the people have higher IQs than I do. My interpretation, if this were the case, would be that I'm an imposter. So I think we can safely say that my IQ is a little bit higher than 82. Where that little bit comes into play, who knows? But you see how we can take the standard deviation and the mean, and it's such a powerful thing when we convert to a set of scores to z-scores and use the standard deviation and the mean to plot out where individual performances fall. One last thing I want to show you here, and that is where these things fall on the normal curve. So what these percentages are, once we convert things to z-scores, notice our z-scores correspond to our standard deviations. A score of -1 is equal to -1 standard deviation. A score of 0 is equal to a 0. A score of +3 is equal to +3 standard deviations. In general, what this normal curve shows us is the percentage of people who fall within each standard deviation. So we can see that typically 34.13% of the population on whatever standardized score we're measuring, once we convert our raw scores to z-scores, we're going to have 34.13% of the population fall within one standard deviation above. More importantly, we can add together the above, below, and get the fact that 68.26% of the people are within positive or minus 1 standard deviation around our mean. Most of the people fall within the mean. We can add all this below, and in theory, even though this is an infinite number, below our mean is equal to 50%, we can see that 84.13% of the people fall within one standard deviation above whatever it is we're studying. They either rank below or above the mean up to one standard deviation. That covers 84.13% of the people in our population. So if we're talking IQs, and we saw that my IQ of 82, my z-score is 1.2, then my IQ really only fell about right here. What we know then, if we know that our standard deviation is 15 for IQ, then, and our mean is 100, 2 standard deviations would mean that 2 times 15 is 30. This would be an IQ of 70 right here. Okay? 3 standard deviations, we would add another 15, or in this case, if we're going negative, we would subtract 15. 3 standard deviations mean this is an IQ of 55. If we were to go the other way, an IQ of 100, 1 standard deviation, this would be an IQ of 115. 2 standard deviations would be an IQ of 130. 3 standard deviations would be an IQ of 145. At this point, you can see that we're over 99% of the population have an IQ of 145. If we were to go to 4 standard deviations out, it would be an IQ of 160. And you can see that 99.99% are going to have IQs less than 160. So if you were to find somebody whose IQ is above 160, they're getting into an extremely rare pool. And in theory, this goes on to infinity. Okay? That's how important and how powerful this tool is. Once we're able to convert raw scores of anything into z-scores, and we know the standard deviation and mean to do that, wow, look how powerful this is. So here are percentile ranks. Notice this is done in a distribution, meaning that there are no negative numbers. There are our z-scores, and then finally our t-score distribution is the same way. There are no negative numbers in the t-score distribution. That's why we call these distributions, because there are no negative numbers. So let's take a look then at what our goals were for this module. So we were going to describe in terms of mean and standard deviation z-scores and t-scores numerical distributions. Given a set of raw scores, we would transform them into their corresponding z-scores. Given a set of z-scores, we could convert them into a distribution of t-scores. Convert a set of z-scores into a distribution of standard scores with any given mean and standard deviation. We really kind of skipped over that, but that's fine. Interpret the meaning of individual standard score relative to the distribution. That's when we started looking at where they fell into percentile ranks. Describe the characteristics of the normal curve. Given a set of z-scores and using characteristics of the normal curve, convert the z-scores into the percentile equivalents. And then finally, given percentile score and using characteristics of the normal curve, transform the percentile to a standard z-score. And that's what we were doing at the end. So your assignment then is this. You will use data from our class and compare height to national averages. Here are important things you need to know. The average male height in the United States is 69.1 inches. The standard deviation is 2.9 inches. The average female height, the mean in the United States, is 63.7 inches. The standard deviation is 2.7 inches. Your job for this assignment will be to convert male and female heights into z-scores, the male and females in our class. No, you'll have one answer for males and one answer for females. Convert them into z-scores. Consider what that means looking at the normal curve. Okay, what I want you to turn in are the z-scores for the males and females, and I'm going to give you some names, some imaginary names, and you can plot them as you wish. You don't even have to plot them; you can just explain them. Based upon the information you have, then analyze the data and give the interpretation of what what you found out about our class heights compared to the national average in the United States. You know, where do we fit into standard deviation 1, +1, -1, +2, -2? Your interpretation: we're a very typical class, or we are an atypical class because of this, and so forth. You know, we're so atypical. We have such tall people in our class that maybe we need to consider raising the door frames. I doubt we'll get that interpretation, but we will see. And you actually have a bonus question with this. Using the distribution charts that I provided, answer these bonus questions. I'm 5'6". If you see me, that's probably not a surprise. What percentage of men in the United States are taller than I am? Your second bonus question: what percentage of men in the United States are between the heights of 5'10" and 6 foot? You can do this. You have all the information and you have worked through it. So you can get both of those little extra points there on your assignment. So we will pick it up from here and move into a new area in our next module.